record, and I shall share my screen. This. There we go. Okay. So, so we just have basically one more problem to do with centripetal motion. What the hell? No idea what's going on. Okay. Which is just a different kind of centripetal motion problem. And then you can ask questions if you need to ask questions on the drag force stuff that you were supposed to teach yourself. And that will probably take us to the end. You can ask any kind of questions that you want at that point. Tomorrow is the test. Monday, remember that you need to teach yourself part of 2.4. There are some videos on the dot product or the scalar product. And remember that we will be using those. So there will be more examples that we do in class that will give you a chance to practice those things. And that reading guide is ready to go. You also need to read 7.1 and maybe 7.2, but those reading guides are not ready. It is my goal to get those done today, and if not, tomorrow during the test, but I figured you'd be studying for the test anyway, so you're not ready to be thinking that far ahead, okay? So let's do our last example here. If somebody would read it for us, please. Okay, so here's whatever my pole thing is. Here's my ball out here. I have a string that goes this way and a string that goes this way. And then the nice thing here is that these are all what I'm going to call L. So what I've got is a equilateral triangle, right? Where L is equal to 1.70 meters. Okay. Doesn't it tell you that? Isn't there a picture? Oh, okay, well then that's what it is. That's what it is. Oh, must have been one of those things that I meant to do and never got back to. Like was labeled the sides. Because I think, yeah, that was it. Sorry. Those are the numbers. I'll fix it. That's not what I want. This is what I want. Okay. All right. And then M is the mass of our ball. And that I gave you, right? It's 1.34 kilograms. Okay. And so what are we going to do? What is the first thing we need to do here? Draw a free body diagram. Okay, so here's my mass, M. Okay, and this thing is spinning around, right? Yeah, spinning this way. Did you ever have one of those toys where you kind of make it go and it spins around? Yes, it's spinning around the rod. So it's spinning around this way. Okay, and the thing is that they're strings. So you kind of have to keep it spinning fast enough so that the strings remain taut. If it wasn't spinning, what would happen? It would just fall and sit there. Okay, so the whole point is that it's moving and that's what keeps it going. Okay, so what are my forces that are acting on M? Okay, so there's how many tensions? 2. So there's a tension that goes off this way that I'm going to call tension 1 because we're told that that is 35 newtons, right? And then there's another tension that goes off that way that we're going to call tension 2. Then I'm going to move the label someplace else. Okay. I can't say that those tensions are equal. There's no reason for me to say that those tensions are equal, especially because there's another force here, right? And what's that other force? Right, the weight or the gravitational force. So there's going to be this Fg. So chances are T1 and T2 are not going to be the same, right? Because if I look at the y direction, the vertical direction, and remember, nothing's happening in the vertical direction. The acceleration is 0. But T1 has to balance out T2 and Fg in that direction. The components do. So T1 and T2 aren't going to be equal. All right, so what's the last thing that we need in a free body diagram? Pardon me? Yes, we need axes, okay? And because this is an object that's moving around in a circle, we want to have positive be towards the center, because that's going to be where the acceleration is. And what kind of acceleration are we going to have? Centripetal, okay? So again, we can call that R, and we can call that Y. Okay. And then what about C and D? I'm sorry, what about B and C? What do they ask us for? Okay, and C is, so tension is an example of a force, right? So if I need forces, what am I going to do? F net equals ma, okay? Which means that I'm probably going to need to break T1 and T2 into components because they are not aligned with my axes. Fg is okay, but T1 and T2 I have to break down. Okay. So what's this angle up here between the top rope and the bottom rope? 60, right? We just said this is a what? An equilateral triangle. Okay. So I'm going to have my components here, T1y, T1r, kind of hard to see. In fact, I'm just going to go to another page and I'm going to make my free body diagram bigger. You do not have to do that. So here's going to be T1, here's going to be T2, here's going to be Fg, here's plus R and plus Y. So you don't have to redo this if your picture is big enough. Okay. So, and then what I'm going to do actually is I'm going to make my components go this way. So this is going to be T1 Y, and this is going to be T1 R. And then I can do the same thing for T2R and T2Y. Okay, we good? And now we can see and read all the labels and all that jazz. All right. So what did we say this angle was? 60. Okay. That horizontal axis bisects that angle. Okay, because it's an equilateral triangle, it's the way it has to work. So that means that this angle down here is what? 30. Which means that this angle is, which means that this angle is 60. Okay. All right. So I have made a wonderful, now accurate free body diagram that I can read. What am I contractually obligated to do next? F net equals ma. Okay, which direction would you like to start with? I have a feeling we're going to need both. R. Okay, so we can say that F net R is going to be equal to ma what? C. Okay, that's going to be the direction of our centripetal acceleration. Okay. So what are my forces in the R direction? Okay, so T1R, T2R. Okay. So T1R and T2R are positive or negative? Positive. So I'm going to have T1R plus T2R is equal to MAC. My centripetal acceleration points towards the center, so it should be positive, and I'm going to leave it positive. Okay. So I know what T1 is, and I'm looking for T2. So I probably want to express T1R and T2R in terms of T1 and T2. So what's T1 going to be? T1R going to be, excuse me. T1 times what? Yeah, but that's going to mess people up. So let's call it sine 60. Okay, which has the same value, but the angle I've labeled is 60. Yeah, depends on your picture. They are the same. If you put sine 60 and cosine 30 into your calculator, you get the same thing. Okay. How about T2R? That's going to be T2 times what? Yeah, but again, I've labeled the 30, so I'm going to make it cosine 30. Okay. I like it that you guys are thinking in all the jazz, but just makes it a little easier for everybody. Okay. So I know what both the angles are. I know what the mass is. I know what T1 is. Do I know what T2 is? No. Do I know what AC is? No. So I have two unknowns, but one equation. So what do I need? I need another equation. Okay. And where do I go to find another equation? Yeah, the y direction. So I'm going to have F net y is equal to MAY, and that's going to be equal to what? 0, right? Because my ball isn't bopping up and down, it's just going around in this level circle. So what are my forces in the y direction, excuse me? So I have T1y plus T2y plus FG, and when I add those all up, have to be equal to 0. Okay, T1y positive or negative? T2y positive or negative? FG positive or negative? Okay. Again, I want to put these in terms of T1 and T2. So how do I write T1y in terms of T1? Cosine 60, yep. How do I write T2y in terms of T2? Sine 30, yep. And then FG is MG. And now I'm doing pretty good, right? Do I know what T1 is? Do I know what T2 is? Do I know what MG is? Yeah, so I know everything except T2. So you do the math and you tell me what T2 is. What do we got? What do you get, Dagny? Annabelle, what did you get? Tia, what did you get? All right. Everybody get that? Okay. So that's great. That's the answer to part A. Or part B, excuse me. What does part C ask us to find? The net force on the ball. What direction is the net force on the ball in? Yes. So is it an R or Y? R. Okay. So really, I want to go back to this statement up here, right? So what I want to figure out is this. F net R1 is equal to T1 sine 60 plus T2 cosine 30. So I'm just going to write that on the next page. But you don't have to. You can just figure that out. T1. So what's F net R going to be equal to? What'd you get? Okay, so I think we've got 2 sig figs, right? Because of the 35, so 38. Cool. I know, Fiona, I switch when I care about sig figs and when I don't, and it's not fair. Apparently I switched in my notes when I cared and when I didn't care either, so my apologies. All right, other people get that? Okay, so then what does part D ask us? The speed. How am I going to get the speed out of this? Okay, so what's F net R equal to? Okay, so this is going to be MAC, and then what's AC, Dagny? V squared over R. Okay, so do I know M? V is what I'm solving for. Do I know R? Can I find R? Yeah, okay, so remember I have this lovely equilateral triangle. Okay. This is the R that I'm looking for. Okay. And it's important to remember that it's the shortest distance from, it's the perpendicular distance, which will be the shortest distance from the object to that axis that it's rotating around. And of course, this will be L over 2. What's this angle up here going to be? 60. Okay, this is going to be 30. So you figure out what R is equal to. Use your geometry skills. You can have an extra sig fig right now. Okay. And we're going to keep an extra sig fig because it's an intermediate answer. It's not the answer, but I don't want rounding to be a problem. So then tell me what the speed's going to be after you've confirmed what R is. Because maybe Fiona's wrong, as hard as that may be to believe. What do we got? Fiona says yes. Others? We getting the math? Okay. So that's what this problem is. All right. Questions. Questions on centripetal motion. Let's start there because we've got about 15 minutes. A little more. You can ask about homework questions. You can ask about anything you want. Well, the way you want to look at it, the guiding principle is your life is easier if you have an axis aligned with the acceleration. Because that's how you're going to use F net equals MA. So if you have a car going around a banked curve, you can tilt your axes if you want, if it makes you happy. But then you have to remember that this horizontal acceleration doesn't point this way, but it's easy. I can't bend my arm the other way. Okay. This horizontal acceleration, you're going to have to break that into components. Okay. And that's just, it's asking for trouble. So yes, but this is why. So don't do it if that doesn't serve the problem. Okay. Other questions on centripetal motion, on centripetal force? Probably not. Number 4, this one? The mop is on the floor. The mop has never, it's not falling, you're pushing the mop along the floor. Okay? You can ask. Well, we were, but does anybody else have a question on centripetal force? Okay, what do you want to ask, Dagny? Yep. Mm-hmm. 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 It should be clear from the problem what's happening. Like there may be those two forces, but they'll tell you it's moving to the left. You know, so that you, because that's asking a lot at this point in your physics career to figure out which way the object is moving and then figure out the friction force on top of it. Like, so it's possible that you would be asked that, and that's the way to go about it. But most likely, if you don't know which way the friction force points, try rereading the problem and then try drawing a picture. Okay.
To clarify, if you do draw a resultant vector, but the question says the object moves to the left, you would just put the friction to the right.
Right, let's take out the part about drawing the resultant vector. But if they're telling you that the object at this point, because it'll change later when we do things that rotate in wheels, okay? But yes, if the object moves to the left, the friction force is to the right. Okay, how about any questions on drag force? Because you did that on your own. I hope you did the experiments I asked you to do. Those were like important. It's what I would have done in class. Oh no, you didn't sacrifice those, did you? Because they had a lot more what? And what? Why? What did they have more? They had a lot more surface area. Okay. So any questions on that drag force stuff? Yeah. Sure. Okay, so here's a pencil. Okay. No matter how I drop this pencil, it has the same mass. Okay, which isn't really a part of this anyway. Okay. But it looks the same as long as I'm dropping it straight down vertically, whether I drop it this way or this way, it's going to have the same effective cross-sectional area. So A is going to be the same. Okay. I'm dropping it through the same air. So that's going to, the density is the same. But I have the equivalent of stone.
I was really Dr. Study doing the biology and I'm so excited. I'm doing it really like listen to the project and we're gonna never. Yeah, I agree. That addiction is responsible for making you like making you. Are you talking about like centripetal motion? Yeah. Yeah, that's kinetic friction is not for tires, so it's static, yeah. Because like I just want to put last questions from my side because I don't think I didn't finish it that well. Okay. But kind of like address it or screen. Yeah, I don't know. I think she's trying to just like kind of vary it to get rid of it. I don't see a grade on it. I just got one thing at the top. That is like not like it. There wasn't out of anything. I didn't even get anything. Yeah, I doubt that. But I just know there's so much content for this, like forces and friction. Like there's so much, spend so much time on it. What is the test gonna be? Oh, I'll throw over to the Oh, thank you. I'm just hoping.
Okay, I can't find the thing that I'm looking for, but this should work. Okay. What else is in this? So it's going to have the same cross-sectional area flowing through the same air, so rho is the same. For short distances, it's going to have the same velocity. Okay. So the thing is that if I drop it this way, where it's flat, into my sand, it kind of falls. Okay. So it kind of bounces, which was a whole other thing. But if I do a pointy side, it sticks more. It sticks more. Okay. And like there's no way, there's nothing in that equation that counts for that. That this end is more aerodynamic, which is why missiles and fish look like this. Okay. Always look like that. I don't know, but as they evolved into multi-celled creatures, if you look at fish, like sharks, you look at anything, they're narrower at the front. Yeah. Life is full of mystery. Okay, there must have been another evolutionary advantage to being that. To have being chemical shark. Okay. So that's that's the best way I can describe C. That's the best example I can give you. Is it some other characteristic that will make a difference? Okay. You will never be given, like you'll, like there, it probably is, but like there's no table for C. You saw the problem you had for homework. You know, it's like we assume that C is the same for this both ways, and when you're going to cancel them, or you're going to find it. But don't get too crazy about it. I think the thing to take away from the drag force is that terminal velocity exists and how we get there. That, you know, it has to be because the drag force increases as the velocity increases, but eventually it's going to like hit this equilibrium point and then it can't accelerate anymore unless something changes.
So the drag force itself reaches a point where it doesn't.
Well, drag force reaches a point where it's as big as the gravitational pull. So now those two forces are the same. If those two forces are the same, then the acceleration is zero. If the acceleration is zero, the velocity can't get any bigger. If the velocity can't get any bigger, the drag force can't get any bigger. So that's why it's terminal velocity. It's the final velocity, the end velocity.
Okay, that makes sense.
Okay, anything else about that? Anything else at all that you want to ask? We still have 6 minutes. I'm gonna take some stuff off so that it will feel more comfortable in the 60 minutes that you have, the 60-ish minutes that you have. You were here yesterday when I apologized for making the first one too long. But yeah, no, I was looking at it last night and woke up and realized that I wanted to fix it.
Should we memorize the equations for Atlas machine, or we can
No.
solve for it because you can like manipulate the equations?
That's one of those things. I personally would never memorize the equations for Atwood's machine. I personally will never have to sit down and answer 35 multiple choice questions in 45 minutes ever again in my life. So I don't care. Any situation I'm going to be in, sans zombies, I can sit down and figure it out. Is there a chance you will get a multiple choice question on the AP exam where it would be useful to have memorized those? Yes. Are you going to have time to sit there and figure it out? Probably, because there's going to be 15 questions that you have no idea how to answer anyway, so you might as well spend your time on this one that you can. Maybe not 15. But, you know, we'll talk about test taking strategy later. If it comes up on a part 2 or it comes up on a question that I'm going to give you, most of my multiple choice questions expect that you're going to do some work and gives you partial credit if you do. So I'm going to want to see the work.
Oh, really?
As we get further on, like the ones in the beginning, were all worth like 1 or 2 points, and like there are no multiple choice questions on this test. But as we keep going, like multiple choice questions start to be like you've got 2 on a page because I expect that you're going to have to do work, and they become worth like 5 points because you have to do the work to do it, and I'm going to give you partial credit for it to get you, because you need to do multiple choice questions because that's what's on the exam, and you have to be ready for that. But if I'm going to give you an Atwood's problem, it's not probably going to be a multiple choice question. It's going to be a figure something out and explain it to me kind of question. So you're probably going to have to quickly show me that you know how to do it anyway. So I think, as with all things, it's more important that you understand the process. You understand how to draw free body diagrams. You understand the way your axes have to go. You understand Newton's second law, and then you've been doing algebra for 10 years, not 10 years, but 5 or 6 years now, and you should be able to do that algebra pretty quick and not make mistakes because it's really not that complicated in terms of algebra. When we get to reviewing for the AP exam and test taking strategies, I highly recommend that you go through the whole test with 3 different kinds of marks. One mark is, I know how to do this. And you probably just do it because some of those questions you're just going to answer. There's a mark for, I know how to do this, but it's going to take me 2 minutes to do all the math. That's one kind of mark. Another kind of mark is, yeah, right. I'll come back if I have time at the end. But you want to make sure that you don't miss question 34 that you can read and go, oh, well, this is the answer. And you want to make sure you have time to go back and do question 15 that, okay, I need 2 minutes to figure out all this math, but I know I can do that. So that's kind of the way. And that's why I say, there'll be 17, 15 questions you can't answer anything, which is true, but there will be questions that you're like, I have no idea. Either because you're having a brain fart, or because you can't put pieces together, or you were sick that day. It's just like, it just happens.
Yeah.
It's just the way it goes. And the same thing will happen with the part 2s. But what's that?
One last question about Newton's third law.
Mm-hmm.
You only use, or you should always draw the forces of the other object in the other. If you have 2 objects in contact, like you should draw the pairs in your free body diagrams for each time search to
Well, I'm concerned about what you're saying. So if I have M1 and M2 and M3, okay, and there's actually something else we should talk about. No, we don't have time. So if I draw a free body diagram for M1, and let's say there's some big force going off that way, okay? So there's going to be a force from 2 on 1 that goes here, FG normal. M2, there's going to be a force from 1 on 2 and a force from 3 on 2. These are a third law pair, but they are acting on different objects and they are in different free body diagrams. Yes, but opposite in direction. Okay, I wasn't sure from what you said about where you were drawing them, and that's what concerned me a little bit.
Oh, thank you. This is
Sure.
what I meant. I just
Okay.
Did you put them in their respective?
Yeah, you have to. They're there. They're real forces, unless you're thinking about the whole object. Like if I'm looking at this whole big thing to find like its acceleration like we did in class, then no, because those forces all become internal forces and they cancel. Okay? And you, Lauren, are supposed to go and eat your lunch, I believe.